Everyone, we'll look at some examples here for calculating the force on moving charges, and then how does that apply to a current carrying wire. Well, in this right here we can see that we've got a velocity of the charge in the positive J direction. There is a magnetic field that is in the positive J and negative K direction. So the question is, where is the force? Well, since we know something about cross products, magnetic force is QV cross B. We know the velocity is in the J direction, so I've got to cross that with another vector that is 90 degrees away from it. Well, J cross J is not going to give us any force, so really J cross K is going to give us our force. So if you do your velocity cross with the magnetic field, you do get negative I for your direction of the force. Well, how much force? Let's say that's a proton there, and if you put in the proton charge, the velocity of 1 times 10 to the 7th, that's still legal, it's under the speed of light, and the magnetic field strength, let's give a magnetic field strength of 1 Tesla, about 1.5 to the negative 11th newtons, or about 15 piconewtons of force. So that's how we solve a problem using Q, V, and B. But what about a current carrying wire? A current carrying wire has moving charges. We know that charges drift through wires, albeit very, very slowly. So do they feel a force in the presence of a magnetic field? So we did a demonstration today with a power supply, a light bulb, and then we have current going through our wires. You can see the current goes down through that little swing and back up. So with having electricity run through there, you can see when the current flows and there's a magnetic field down, there's current heading in one direction, the force is acting on that current carrying wire. When I reverse the current, moving charges are moving in a magnetic field, and they feel a force when the current is flowing. When the current turns off, then you can see that the force disappears on the wire. A way that we can visualize what we're seeing here is with this drawing. So I have a very strong north and south pole magnet, so the field points away from north towards south. I had a current carrying wire there, and let's say the current was heading right towards me. So I have the current coming straight towards you. What that does is it creates its own magnetic field in a loop using your first right-hand rule like this. So we have a loop of magnetic field in an external magnetic field. And we know that magnetic fields interact with each other. They'll either attract or repel each other. So in this case, with a moving charge, that moving charge is coming towards you. The magnetic field is down. So if you do your V cross B, you get a force outwards that deflects that wire out towards me. So with having a magnetic field and a current carrying wire moving charges, they feel forces, and that whole swing kicked out. If we reverse the current, send current into the page now using your second right-hand rule, you get magnetic fields to go in this direction. And when you have magnetic fields going in the opposite direction, they now will feel forces differently. We have moving charges into the page. You can see the magnetic field is still down from the permanent magnets, and now we get a magnetic force pointing to the left. So that current carrying wire has a force on it due to moving charges. So if I write our force equation, remember that force equation is QV cross B. This time we're going to use the drift speed to be the velocity of the moving charges. But if you look back to that current carrying wire, there's more than one charge is moving. There's multiple charges moving through the wire. And if we do that, we should write our equation like this. NQV cross B, where N is the amount of charges moving in a particular volume. Q is the charge of one of those positives or negatives moving through the wire. Remember, V is the drift speed, and B is the magnetic field. But since little n is the charges per volume, we need to kind of get rid of that volume so that we just get the number of charges. So to get rid of a volume, the volume of a wire, you can see here, would be the area of the wire multiplied by the length of this wire, since you can treat the wires like a cylinder. So I'm going to add one more term to our equation. So NQV multiplied by the volume of that wire, which is the area of the wire multiplied by the length. Now, looking back at our equation sheet, N, Q, V, and A have all been used before to describe the movement of charges through wires. And if you look back to your equation sheet there, all four of those end up being the current. The current passing through a wire feels forces because you can sum up all the charges that are drifting through that wire and treat them as one charge. So our final equation for the forces on a current carrying wire ends up like this. It's the force equals the current times the length cross B, or Filb. The force on a current carrying wire is Filb, F-I-L-B. I now being the movement of your charge, L being the length of your wire, and B being the magnetic field. So we can apply the right-hand rule here again. IL we call the current element. This is where you put your fingers. The magnetic field is where you're going to curl your hand. So you curl into the direction of the magnetic field, and your thumb ends up being the force. So it's just like the moving charges. You put your fingers in the direction of the velocity, you curled in the direction of the magnetic field, and your thumb told you the force. Same thing here, but now with a current carrying wire. One thing we did discuss in class was people said, well, positive charges aren't really flowing through a wire. It's electrons that are actually flowing, and that is true. Electrons are flowing in the opposite direction. So let's apply the right-hand rule again, but now with electrons going in the opposite directions. Let's give us a magnetic field, say, up. So I have a magnetic field up, and I have charges moving through this wire. If I go with a positive conventional flow of current, we'll say it's from left to right. And if you want to say it's the flow of electrons, we'll say the electrons are going from right to left. Well, using our Filb equation, you put your fingers in the direction of I, you curl in the direction of B, and you get a force that acts out of the page. So the force is acting out towards me if you put your hands in the direction of conventional current. However, the electron is what's actually moving. And when you do electrons, you don't use your right-hand rule because electrons are oppositely charged from positives. So if you do the left-hand rule, put your fingers in the direction of the electron moving, curl, your thumb still comes out of the page. So positive charges, you use the right-hand rule, and negative charges, we use a left-hand rule. If I switch the direction of these currents, and I make the current flow from right to left, now the force, if you do your I cross B, put your fingers in the direction of current, curl with the magnetic field, now you get a force into the page using the positive flow of charge. But now, since we're having current flow in the opposite directions, electrons flow against that. So electrons go the opposite way. Using left-hand rule, V cross B gives you a force into the page as well. So either way you do it, right hand or left hand again for positive charges and left hand for negative charges. So there's the equation you can write there. Filb is IL cross B. Remember, IL is what we call your current element. And yes, just like for moving charges at angles, you can also have moving currents at angles to the magnetic field. Again, since it's a cross product, only when you have two vectors that are 90 degrees apart will you get a third vector, which is your force on the moving charges. But what about something like this? When we look at something like this, we've got moving charges that are going up and over, and we bent that wire into a semicircle. So the magnetic field's coming out towards us, and we've got this current carrying wire changing direction as it goes through that loop. What direction will the force be? So let me redraw this and show you how we solve it. Alright, so here's your setup here. We've got a magnetic field with a half a semicircle of current flowing through it. The question is, what forces and what direction of force does each of those segments of the wire feel? The first thing you want to think of is the current heading up the semicircle. So if you put your hands in the direction of current and you curl with the magnetic field, the blue dots there represent magnetic field coming towards you. What you see is that you get a magnetic force that points off in this direction. Let's look somewhere else. At the next segment of the wire, here's your current. And if you put your fingers in the direction of current, curl in the direction of the magnetic field, you get another magnetic force that points like this. Moving along your wire, if you pick a couple other locations and do your IL cross B, you get magnetic forces to point in all directions outward from the line. If we sent current in the opposite direction, all the forces would be inward. If I want to find the total force that this semicircle feels, what I have to do is I have to add up the force all the way around the loop. I have to find the force at each little segment as I go over and across this semicircle. Let's focus on a little bit of a current element right here. That current is a certain radius away from the center of my semicircle, and I've made an angle theta when I've made it to this point of my loop. Segment closer of a much smaller theta, but the nice thing that's constant there is the r. So when I want to write my force equation, remember the force on a current carrying wire is I L cross B. And in this case, I'm going to take little pieces of the length and multiply by my magnetic field strength all the way around my loop. At this location that I've picked already, I've got a DL that points in the direction of current. There's my little DL. And that DL has two pieces to it. It's got an X component and a Y component. And the nice thing is that this angle right here, theta, is going to be the same angle as this piece down here. So those two angles being the same, I can write out a triangle for my DL. A dx and a dy component that change as I go up and around that length. When I get to the top and I look at the DL along the top of the wire, the DL is just in the x direction. As I come back down, the dy is negative as I pick different pieces of those wire. So I've got to add up each of those forces on each little current element throughout the loop. So a way that I could write DL in terms of its vector notation, I could write DL as negative DL sine of theta in the I direction. And the reason it's negative is you can see that I'm pointing to the left as I move across my wire. And I'm going to add in DL cosine of theta for my J direction. And the reason that's positive, again, is because I'm dealing with this segment right here. So if I'm going to put that in for my DL, let's see what happens. So there's our force equation now. It looks pretty gross. It's I dl sine of theta in the I direction plus dl cosine of theta in the J direction cross magnetic field. Now the magnetic field, remember, is in the positive K direction because the magnetic field's coming out towards you. So when I cross the magnetic field with those two dl's, I'm actually going to get a vector. But right now I can't really integrate because I have dl and I also have sine of theta. I have two things changing. I have that little length changing and I have the angle changing at each moment. So that's why we want to look at that in terms of a constant, and the only constant here is the radius. So if I want to write an equation in terms of the radius, what I can say is dl over d theta is equal to the constant, which is the radius there. And I can rewrite an equation for dl by multiplying d theta to the top here and then substituting that in for wherever dl is in my equation. So it's going to get stretched out one more time. I'm going to pull out all the constants here. So there's our setup. Now one thing I want to do here is figure out which direction the force is going to be. So if I do k cross a negative I, k cross a negative I gives me positive j for my sine component, and k cross j gives me positive I for my y component. So now if I want to do this and I want to solve for the force, I've got to integrate the force all the way around the loop. That means I've got to integrate both of these, the sine and cosine. So integrating sine and cosine there, sine, so here's our setup. We're going to integrate both the sine and cosine of theta from two bounds. If you look at our two bounds will be from right when the current comes in at 0 degrees as it goes all the way around to here, or 180 degrees, or if we write that in terms of pi, from 0 to pi. So let's make sure we integrate both of those. Integrating sine, you'll get IRB cosine. I'm going to put in 0 and pi there as my two bounds. And integrating cosine, one thing we can do here is put in our two bounds for sine. Sine of 0 is 0, and sine of 180, or pi, is also 0. So this whole section here goes away. So I actually don't have to worry about any component in the I direction whatsoever. It looks like my final force is going to be in the J direction. So now let's put our bounds in there. If I put in pi of cosine, I get negative 1. So minus a minus 1 is positive 1, minus our other bound. Our other bound is 0, so cosine of 0 is 1. So minus a minus 1 gives you a plus. You end up with 2 in the end. So the force on this current carrying wire on this loop ends up being 2 times the current times the radius of the wire times magnetic field strength. And that's the total force the wire would feel, 2 IRB. But you could say then, well, what would happen if we had an entire loop? What if the wire continued in an entire loop and the current went back out the same direction? Well, if you look at it, you get forces that were out in all directions, and if you add up all those forces, you'd end up with 0 if you completed the entire circle. So having force on the entire loop would actually cancel out to nothing, where this is the force on a semicircle in a magnetic field. So I hope you can follow through that derivation, and we'll talk more next time.